Welcome again. In this video I'm going to talk about the so-called Miller indices. Miller indices is basically a system which is used to describe planes within a crystal or a space lattice that specifies orientation without giving position in space. So this system is based on the intercepts of a plane with the three crystal axes, so basically the three edges of the unit cell. So in this video I will show you how to determine the Miller indices in the unit cell. I will show you some interesting things, and I will also draw some cells, especially for the face-centered cubic system, so you can understand the slip planes and the slip systems better. So basically there is a set of rules which you can follow to describe or determine the Miller indices. So let's talk about this first. So determining Miller indices. So first of all, let's make it first. What we have to do is we have to find the intercepts on the three axes in multiples or fractions of the unit distances on each axis. So I write it down. This might be a bit slow, but so first we have to find interceptions So first we have to find the intercepts on the three axes in multiples or fractions of the unit distances on each axis. And then once we have this, we have three numbers. We have to take the reciprocals of these. So something like 1 over A, 1 over B, 1 over C, where A, B, C is the vectors for the unit cell, so the unit vectors. So we have this. We have three numbers. We have to reduce this to the three smallest integers having the same ratio. So reduce to the three smallest integers having the same ratio. And then we just finally enclose it in parentheses. So something like and we have the 3 dots, the 3 numbers. For Miller indices we use H, K and L. So H, K and L. So for example we have a unit cell here. I try to draw it nicely. So we have our unit cell. So let me draw the 3 axes in red. So each of these distance at this corner, and this corner is 1 because it's unit. And then let's call this X, Y and Z, or L, K and H. So for example, if we want to draw, let's say 1, 1, 1, then we do the following. So we start from the 0, 0, 0, right? And then this is H, so we move 1 on the H axis. And then K, we move 1 on the K or Y. And then L, so we move 1 on this. And then we just connect these 3 dots. And these are not body diagonals, but they go on the face of the cube, like this, and this is also. So then this plane here, this is the 1, 1, 1 plane. And you can also approach this from a different perspective. I will try to show you as well. But in cubic systems, these 3 numbers are basically the numbers of the, or these 3 numbers is the vector for the normal of the plane. So therefore, if you have your coordinate system here, and then we go back to the 1, 1, 1, but now from a different perspective. So we start from 0, and then these 3 numbers say that move 1 unit on the x-axis or x direction, and then you move 1 in the y direction, and you move 1 more in the z direction, so you end up at this corner. So basically you will have 2 points. You have your initial point, let's call it O, and then you have your final point, let's call it P. So basically, if you connect these two, which now is the body diagonal, this is actually the normal vector of the plane, which is in this case is the 1, 1, 1 plane. So if you go back to the previous figure, then the arrow actually, you can see, it's not nice because it's 2-dimensional drawing, but you can see that basically the OP vector is perpendicular to the 1, 1, 1 plane. So the 1, 1, 1 vector is the normal vector of the plane, the 1, 1, 1 plane. So you can construct the planes in 2 different methods. The first method is basically you step on each axis, or you just mark the intersections. So if you have 1, 1, 1, then you mark all the 3 intersections, and then you just connect the dots or the markings. Or you can think about this as a vector. So you start from your origin, which is the O here, and then you check what is inside your parentheses. And we have 3 1s here, so that means that we have to step 1 unit in each direction. So therefore we step first 1 in the x direction, and then from that direction, we step 1 in the y direction, and then we step 1 in the z direction, and then we obtain the P point here, and we just connect the O with the P, and that will be the normal vector of the 1, 1, 1 plane. So this is also a method to obtain the plane from the Miller index, or from the Miller indices. And then just another example. For example, we have the cube here. It's a bit skewed, but so cube, and then we add the coordinate system just to make it better. Z and X. And now let's say that we just want to draw the 1, 0, 0, which means that we step 1 on the X direction, and 0 on the Y direction, and also 0 on the Z direction. So therefore we just have this, and this will lead us to this plane on the face. So this is the 1, 0, 0 plane, and if you see the intersections, then in X direction we intersect at the position 1, but in the Y direction we intersect in the infinite, and then in Z direction we also in infinite. And then so we find the 3 intercepts, so we go back to the rule number 1. So therefore we just write down like 1, and then infinite because of this, and infinite, and then we take the reciprocals, so 1 over 1, and then 1 over infinite, 1 over infinite, right? So this will be 1, this will be 0, this will be 0, right? So this is done, this is done, this is done. So HKL, sorry, L. So this is 1, 0, 0. So it's quite simple. So we saw how we can draw some planes, but we have to consider some notations. So there can be negative intersection, so we will just find the intersection in the negative direction, but the notation looks a bit different. So when there is a negative number, then we just put a line over it, so it's an overline and not a negative sign. So not like this. We always use overline if it's negative. And then we should fix the parentheses, how they work. So there are 4 different notations. If you have HKL in these round parentheses, that means that it's a single plane or set of parallel planes. It's a single plane or set of parallel planes. Then if you see like this with brace or curly parentheses, that means that these are the equivalent planes. So if you see, for example, 1 0 0, then in fact that is 6 planes, or in total. So it includes the 1 0 0 plane, and it includes the 0 1 0 plane, and then 0 0 1, and then here comes the negative, so -1 0 0, and 0 -1 0, and 0 0 -1. So the braces are for equivalent planes. And then if you see rectangular parentheses, that's indices for direction. And then if you see these brackets, then full set of equivalent direction. So these two guys here are directions, and these two guys here are the planes. So for planes we have more like curved parentheses or curly, and then for directions we have like rectangular or straight lines. And then let's talk about the directions a little bit. So we have our cube, just to draw a little bit again, and then let's put the coordinate system, x, y, or z. So the directions are basically, the plane was HKL, and the direction is U, V, W. And then if we use this cube, then let's say this direction is the 1 0 0 direction, and then this direction is 1 1 0 direction. And what else we have? Let's say this. So here we have 0 1 0 direction. We can come to this direction. This is 0 0 1, and then let's come from here to the corner, and this is of course the well-known 1 1 1 direction. And in cubic systems, but only in cubic, in hexagonal system it doesn't work, but in cubic systems we know that HKL is perpendicular to the U and V and W. So these are, and yeah, we can prove this. So let's go back to the cube, and we have our 1 1 1 plane. Now I use this nice green. So these are face diagonals which we draw. So we have the 1 1 1 plane, and we have the 1 1 1 direction. So just to make it clear, 1 1 1, and we use the blue here. 1 1 1, right? So we can check the following. We can check the angle of these two vectors, right? So we have this rule, like cosine alpha equals with AB divided by the magnitude of A times B. So up here, this is basically a dot product, right? So A1 times B1 plus A2 times B2 plus A3 times B3, which is basically 1 times 1 plus 1 times 1 plus 1 times 1, which is 3, right? And then here is just the square root of A1 squared plus A2 squared plus A3 squared, which is basically the square root of 3. And of course B has the same. Basically, let's call this A and let's call this B. So we do this. And now this will be just simply 1. So if we do the inverse of this, this will be 0 degrees, which means that the normal of the plane, so the normal of this triangle, the 1, 1, 1 plane, is parallel to the 1, 1, 1 direction. Of course it's parallel because the normal of the plane is itself this direction. And then if the angle is 0, that means that they are parallel, right? So we can say that A is parallel to B. So the normal vector of the plane is parallel to the to the direction of the 1, 1, 1 vector. And in cubic system it always works like this. So we can do a little bit of practice. So I will draw some cubes again, just like this. So I will show you a few planes and then you can try to reproduce everything. So it's more or less nice. And let me copy and paste everything. So let's make it like this. And let's practice. So I choose blue. So here let's try 1, 1, 0. So basically 1 at the x, 1 at the y, and 0 at the z. So we just connect these. So these are face diagonals again. I just cannot really draw a straight line. So this is what we have. Or you can always also think about the normal vectors. So you go one direction or 1 unit step on the x direction, 1 unit step on the y direction, and this will be P and the origin is O, so you connect it, so you have this vector, and you see immediately that the OP vector is perpendicular to the plane that we just drew here, so to the 1, 1, 0 plane. So therefore this 1, 1, 0 vector automatically becomes the normal vector of the plane. But this is only valid for cubic systems. And we can do this, for example. So we saw that 1 at the x, 0 at the y direction, and 1 at the z. So again, face diagonal, and then face diagonal. So this will be here, and this is the 1, 0, 1 plane. So yeah, and we can try to do the same as previously. So we came one step here, and no steps on the y direction, and one step on the z direction. So we end up here, and we connect this with the origin. So we have O and P. We connect O to P like this, and you see that these are also perpendicular, because these are basically, this is an A times A square, and then if you cross the diagonals, they are perpendicular. They should be perpendicular to each other. So let's continue with something else. 0, 1, 1. So basically what we have here, x, we stay at home, y is 1, z also 1. So we come here, face diagonal, and face diagonal again, and let's connect this. It's a bit ugly, but I think you get it. And we can also do the practice. So 0, and we came 1, and we came 1, and then I messed up. So we can draw 0, 1, 1. So 0 at the x, 1 at the y, and 1 at the z. So we just connect it here and there, and then we do our other strategy. So 0, 1, 1, and then we see that O to P is also perpendicular. We can try 1, 0, 0. I showed this already, but we can repeat. So basically we just have one intersection here, this face here, and then of course this is very simple. So we start from the origin, we come to this P point. Of course, I mean, if we have an imaginary vector here, this will be perpendicular to this plane. It's very simple. And just the other planes, this will be quick. So 1, 0, 1 is basically 0, 1, 0. So this is 0, this is 1, and this is 0 again. So we just draw it like this, and then just to show the other direction, 0, 0, 1. So 0 in this direction, 0 in this direction, and 1 in this direction. So, and you can use other examples just to practice and find the planes. And here what I want to show you is I think a very important thing for face-centered cubic systems. So FCC system. So I just want to show you how the slip plane and the slip directions are created in the FCC cell. So I draw again, just cell here, like this, and then I draw my vectors like this and like this. So I draw a few atoms to show the FCC cell. So we have atom in the corner, right? And then we have atom on the face on the XZ plane. So there is one here, and then in this corner, and then I put another atom on the ZY plane somewhere there, and then one in this corner, and then another face is the XY plane, so this. So what I do here is, let's connect these things. These are the face diagonals. So I show you all the atoms which are involved with the 1-1-1 plane. Why? Because the 1-1-1 plane is the most densely packed plane in the FCC system. Maybe I did not write this correctly, but I don't know how to write it. Most densely packed slip plane. So this is very interesting for us, the 1-1-1. And then if we just pick out this triangle, so we can see that we have one atom here, this guy, A, B, C, just to make it more simple, A, and then another atom here, and another atom here, 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 here. They should touch more evenly, but I think you can understand. So I draw you another triangle, now a bigger one, which will represent the 1-1-1 plane. And as we know that there are 4 independent slip planes in FCC crystal, and within each slip planes there are 3 independent slip directions, and this is how we get the 12 slip systems. So what I want to show you is how we find the slip directions in the 1-1-1 slip plane. So we have our triangle with the 3 corners of it, and then we know that there are 3 directions, and we just follow the line of we just follow the edge of the triangle like this, and we know that within the 1-1-1 we have -1, 0, 1 direction, and then 0, -1, 0 direction, which is this, and then we have 0, -1, 1 direction. But how do we get this? So I draw a cube again, like this, and we need our vectors. And since there are 3, I just want to copy paste this 3 times. So let me write down, let's make this one, and sorry, yes. Yeah, I messed up this. So the B direction is -1, 1, 0. Sorry. So let's show the 1, 1, 1 plane first. So you see everything. So this is the triangle within the cube. And then we try to find the -1, 0, 1 direction. So which means that in x direction we have to move in the -1. So basically we can just go in this direction towards the -1 direction and put our first point there. And then we don't move in the y direction, but we move in the z direction 1. So we have something in the background which I don't want to draw, or I can try. So we have something like this. But since these planes are we can shift these planes because this is a set of parallel planes, then basically we have something like this. So I just shifted back the plane just by 1 unit. So we have the plane like this, and therefore the direction is the normal of the plane, which goes in this direction exactly. So then we see that this is basically this. Of course it can move in the other direction as well. So, but plus minus we don't care about that at this moment. And then we can have the second one. So we have our 1, 1, 1 here. And then we say that here 0, the x or the h, and then -1. So instead of this direction we move in the other direction, like in the imaginary direction here. And then 1 in the z direction, so here. So in principle we have something like this and something like this, so outside the cube, but we can shift it back, so basically it starts here. So these are like face diagonals, but it's really difficult to draw it on the board. And then you can see that this goes in this direction. So therefore this and this corner. So it's this direction here. And then we have the final one, -1, 1, 0. So again 1, 1, 1 plane. And then -1, so imaginary direction here, and 1, so we go in this direction, and then 0 on z. So basically we have something here, but we can shift it inside the cell because these are equivalent. So we have something coming across the body. And then of course if we check the this line is not so nice, but yes, it's better. So if we check the normal of this plane, then we see that the normal is parallel with the xy line. So therefore it will be this direction. So just once more again to make it clear. So for the first direction, -1, 0, 1, we have the 1, 1, 1 plane, and then we draw the -1, 0, 1 direction, or the plane as well, because the normal of the plane is the same. So we have the plane, and then we see that we have the normal, which is basically the x to the z, and then that is the same as a to the c. So we are along this line here. And then on the other, we have 1, 1, 1 plane, and then -0, -1, 1. So therefore we will get the normal of this plane parallel to the y to the z, which is the same as b to the c. So basically this line, or this edge of the triangle here. And then in the last example we have -1, 1, 0. So we have the normal of the plane from x towards the y direction, which is basically a to b on the triangle. So that is this direction. And then these can be interchanged, so plus or minus, tension or compression, basically. So this is how you construct the 3 slip directions in the FCC 111 plane. So this is how the dislocation glide proceeds. So when you deform your crystal and it deforms on the 111 plane, then the system will choose one of these 3 or 6 directions in the 111 plane and will go in some direction. So I hope I did not make any mistakes. If yes, then let me know in the comments and I will try to correct those mistakes, but it should be fine, more or less. So if you like this video, just do as you would do usually. Just leave a comment or like, or just subscribe, and I will try to make more and more tutorials on these kind of topics. So thank you for your attention, and see you next time.